in a previous lecture, I made this claim that if you look at the Eisenstein series at the cusp infinity, and for the z argument you have this scaling matrix at 0, and you have S chi, then this is equal to the Eisenstein series at the cusp 0. We have just a z and an s, but you have to put a bar over your character. So here, this sigma 0 is the scaling matrix at 0, and I said that we could take the matrix as such to be sigma naught. In other contexts, this is known as the Fricke involution. And if you square this matrix, you get minus the identity, and minus the identity acts as the identity on the upper half plane. So that is the sense in which it is an involution. So in this lecture, I'm going to prove this claim, and it involves some manipulations with the series definitions of the Eisenstein series, and some thinking about the group structure of gamma naught n. So it can be useful for in situations which require similar sorts of thinking. So the first thing that I'm going to do is I'm going to justify this claim that over here you can replace this sigma naught with a sigma naught inverse and change nothing else. And the reason this is so is because you can compute that the inverse of this matrix is the same thing but with a minus sign in front of everything. And that means that it acts the same way on the upper half plane, right? That sigma naught z is equal to sigma naught inverse z. So we can make this change, and that's going to make the calculation more straightforward. So now let's just write down our definition of the left-hand side with this change. So this is a sum, and here, maybe I'll write a little bit more explicitly. This is a sum over gamma ranging over coset representatives of the quotient gamma infinity mod gamma naught n. So this is not a group because gamma infinity is not normal, but it is some set. And then here we have our chi bar, and then here we have the imaginary part of, and I'm going to insert a sigma naught inverse sigma naught here, and then for the gamma, I'm going to write it as the actual coset, like this. And then we have this sigma naught inverse coming from what we put in front of the z, and then we have our z all to the s. And now what is this? What are we looking at? Well, recall that essentially by definition of the scaling matrix, we have that sigma naught gamma inverse sigma naught inverse is the stabilizer of the cusp 0. And so that means that here we have a sum over gamma coset representatives of this quotient. Here we have our character, and now we have the imaginary part, and just inserting a this definition here. We have the imaginary part of sigma naught inverse times the stabilizer of the cusp 0 times sigma naught gamma sigma naught inverse z, all to the s. And now what we'd like to do is to say that these cosets of gamma naught in fact range over all the cosets of gamma naught, and they get each one once. So really what we're asking is the set, or the multiset, gamma naught times sigma naught gamma sigma naught inverse, where gamma ranges over the coset representatives that we've chosen of gamma infinity mod gamma naught n, does this set equal a set of coset representatives for gamma naught mod the stabilizer at 0? And the answer is going to turn out to be yes, so let's see that. So first, we're going to show that there's an injection. So suppose that gamma naught times sigma naught gamma 1 sigma naught inverse is equal to the set gamma naught sigma naught gamma 2 sigma naught inverse. Well, this implies that sigma naught gamma 1 gamma 2 inverse sigma naught inverse is in the set gamma naught, and this in turn implies by this fact that gamma 1 gamma 2 inverse is in the subgroup gamma infinity. Now, because we're summing over coset representatives, that means that gamma 1 is equal to gamma 2, so if chosen among our coset reps. Right? Because otherwise we would be getting the same gamma infinity coset twice in our original sum, which we're not doing. Okay, so this means that at least there's an injection. What about a surjection? So for that, we're going to have to do a little bit of calculation. So if you just calculate sigma naught times ABCD, instead of writing sigma naught, I will write out the actual matrix. I think that's clear. So if you have the actual matrix, square root n minus 1 over square root n, and you multiply that by just, here I'm thinking of this as being some element of gamma naught n now, any element. And you conjugate it by sigma naught. After just multiplying out these matrices, you find that you get the matrix D minus C over N minus NB A. And this is going to be, again, a matrix in gamma naught n, because for the original thing to be a matrix in gamma naught n, C had to be divisible by n. So this is, again, divisible by n. And similarly, this is going to be divisible by n. And moreover, this is a bijection. So gamma maps to sigma naught gamma sigma naught inverse is a bijection. Because if ever you had a matrix any matrix in gamma naught n, you could always write it in this form, right? This ranges over all integers, right? The C ranged over integers divisible by n, so just minus that divided by n ranges over all integers, and similarly this ranges over all integers divisible by n if B originally ranged over all integers, and you can see that the determinant is still AD minus BC, so it's still an element of gamma naught n, etc., etc. So check this is a bijection, and what that means is that that in this question above of are these the same, well, you must have a surjection onto the set of cosets here, right? Because if you had some coset, you could write it like this. You could write it as gamma naught times something, and you'd have to find that something in one of the cosets essentially of gamma infinity, right? Where if you think of it as just a set of elements in the group, right? The set of elements in the group that contains this group element, sigma naught gamma, sigma naught inverse, it had to be in one of the cosets, and so you're going to get all the cosets of gamma naught n mod gamma naught. So what that means is that our thing, when we write it, we can write it, in fact, as a sum over gamma naught times gamma in this quotient. And so here what we're doing essentially is we're making this change of variables. Gamma goes to undoing this conjugation. So here we have our coset sigma naught gamma sigma naught inverse. The inverses are the way. The inverse is where you put the inverse doesn't matter here, because you're going to end up getting the same value at the character. So you have a conjugate here, and then you have this imaginary part, and we had a sigma naught inverse right here, and then we had our cosets. So now we've made this change of variables, or the inverse of this change of variables, right? And so we just have our coset as such, and then we just have a z here. And this is writing this in a more reasonable way. This is going to be gamma in the quotient gamma naught n mod gamma naught. And then here, what we have is, if we look at the matrix of gamma conjugated by these, right? It's the same as this calculation, because you just have a -1 in front of this and a -1 in front of this, and of course you can just bring those out, and so you have identity squared, which is identity. So you get the same thing, and the bottom right entry here is A. So you have chi bar of A here, the imaginary part of sigma naught inverse gamma z to the s. Now, an observation that we can make is that AD minus BC is 1 because gamma naught n is a subgroup of SL2Z. And we also have this observation that n divides C, because that's the definition of gamma naught n. And what these two facts together imply is that A is equal to D inverse mod n, right? Because this term doesn't appear, so you have AD equals 1 mod n. So this chi of A is chi of D inverse. And it's conjugated. So these two inverses essentially, they cancel each other out, because that's how Dirichlet characters work. So we get this character, but there's no conjugate anymore. And then we have the imaginary part of sigma naught inverse gamma z to the s, and this is indeed, by definition, the Eisenstein series ZS chi bar. So the chi bar, because in our definition of the Eisenstein series, if you have a chi here, then you have a chi bar in the series definition. So if you have just a chi in the series, then you need a bar in the notation on the left.